Problem number 5. So here we have second derivative of y with respect to t plus the first derivative of y with respect to t squared plus xy is equals to 0. When we look at this particular differential equation, we notice that the highest order differential coefficient is d squared y over dt squared. So that means the order is going to be equals to 2 and its degree is 1, so the degree will be equals to 1. And it's going to be a non-linear differential equation because if we look at the second term, we have a square in the power, so that makes it non-linear in nature. Problem number 6. So we have cube root of the second derivative of y with respect to x equals to square root of the first derivative of y with respect to x. What we can do here is we can rewrite this differential equation as the second derivative of y with respect to x whole raised to the power of 1/3 is equals to dy over dx whole raised to the power of half. Now if we take the least common multiple of 2 and 3, so that is 6, what we are going to do, we're going to raise the power to 6 for both sides, so that is going to give us d squared y over dx squared 1/3 the second derivative of y with respect to x raised to the power of 1/3 whole raised to the power of 6 equals to first derivative of y with respect to x raised to the power of half whole raised to the power of 6. And that is going to finally give us the second derivative of y with respect to x whole raised to the power of 2 equals to the first derivative of y with respect to x whole raised to the power of 3. Now we look at the simplified differential equation. We see that the highest order differential coefficient here is d squared y over dx squared, so the order is going to be equals to 2, and if we look at its part, so that is 2, so degree is going to be equals to 2, and it's going to be a non-linear differential equation. Problem number 7. Here we have the fourth derivative of y with respect to x is equals to c plus the first derivative of y with respect to x squared whole raised to the power of 3 over 2. Now since we have a radical term on the right hand side, we need to reduce it. That is going to be done by squaring both sides. We have the fourth derivative of y with respect to x whole squared is equals to c plus derivative of y with respect to x squared whole raised to the power of 3. Now if we look at this particular differential equation, we see that the highest order differential coefficient is fourth derivative of y with respect to x. So the order is going to be equals to 4 and the degree is going to be equals to 2. And talking about the linearity, it's going to be a non-linear differential equation. That is because we cannot write the given differential equation as a polynomial in derivatives. Number 8. So here we have square root of 1 plus derivative of y with respect to x squared equals to x plus derivative of y with respect to x. So first we need to get rid of the square root term which is on the left hand side. To do that, we are going to square both sides. Then that is going to give us 1 plus derivative of y with respect to x squared is equals to x plus dy over dx whole squared. The order of the differential equation is going to be equals to 1. That is because the highest order differential coefficient in this equation is derivative of y with respect to x. However, the degree is not going to be equals to 2. In order to find out the degree, we need to expand the term on the right hand side. That is going to give us 1 plus derivative of y with respect to x squared is equals to x squared plus 2x times dy over dx plus derivative of y with respect to x whole squared. Now we can cancel out derivative of y with respect to x whole squared from both sides, and when we rearrange the terms, we are going to get 2x times derivative of y with respect to x plus x squared minus 1 is equals to 0. So actually the degree is 1 and not 2. So sometimes we need to simplify the differential equations in order to find out its degree. And it's going to be a linear differential equation because this differential equation can be expressed as a polynomial in derivatives.